Welcome to module number 2, cumulative review. As always, thanks for tuning in. As with module number 1 review, the questions themselves are not going to match up word for word with what you have in your booklet, but the concepts can still be applied, and certainly the things I'm going to show you here are going to match up with each question that you have at home. On your particular booklet, you're reading that Ryan is divvying up turkey breast. Here I have Shelley with 4/5 of a pound of potato salad, and it's being split between 3 friends. And once again, we're going to show the model of dividing fractions using a fraction bar. Before we do that, as usual, I want you to read the question and get a feel for what the question is asking us. And you want to say to yourself, if I have 4/5 of a pound of potato salad, which is less than 1 pound, and you're going to split up that fraction between 3 friends, you want to realize that we're creating an answer that's going to be less than 4/5. We're taking 4/5 and splitting that up further. So you want to kind of get a visual in your head that you're taking a fraction and dividing it further. So inevitably our final answer is going to be less than 4/5. So here's how we did this back in module number 2. We have a fraction bar showing here all 5 segments, of which we're going to shade lightly 4 out of 5. Like that. That model is now showing my potato salad 4/5. I'm going to split that up between 3 friends. Now on yours, you have 3/4, so you've got to make a fraction bar that's four segments long, and you're going to shade 3 out of 4. I have to take my 4/5 and divvy it up between 3 friends. Well, how do I do that? I'm going to take my entire tape diagram, my entire fraction bar, and I'm going to divide it up into thirds. And I'm going to do that by putting 2 lines through my fraction bar. So now what I have here is there's a third, there's another friend, there's another friend. Now, as you may recall, we're going to now look at the numerator. The numerator is going to tell me how many out of all of these pieces now, because what I've done is I've created 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I've created 15 segments. I'm going to circle those 4 out of 15. That's what our answer becomes now. It is now 4 out of a total of 15 pieces. So 4/15 becomes our answer. We can check this by using keep, change, flip, which you will be doing regularly in the middle of this review packet. Here's how we can check it. I take my original 4/5 and I'm dividing that among 3 friends, which is an improper fraction of 3/1. Here's how keep, change, flip works. We keep the first fraction as 4/5. We change division to multiplication, and we flip 3/1 to its reciprocal, which is 1/3. And now what you're going to do is multiply your numerators. 4 times 1, which is 4, and 5 times 3, which is 15, and the answer does indeed check out. So you can always check your fraction bars with keep, change, flip. Number 2 is just like number 1. It's just not a word problem. And I'm not giving you a fraction bar to start off with. I want to see if you can create one on your own and then perform the division. In my particular example, I have 3/5 divided by 3. and I believe on yours it's 2/7 divided by 4. This first fraction is going to be the model for my fraction bar. I'm going to make 5 segments. And I'm going to shade 3 of those. That's now modeling 3/5. My whole number tells me that I need to divide all of my segments into thirds, much like I did on the first one. So I'm going to do that by drawing lines through my fraction bar. And then my numerator of my first fraction tells me how many pieces to circle, which is 3. Those 3 pieces represent 3 out of an entire amount of 15 pieces, which is 3/15. Now we can reduce that to 1/5, but for right now, let's just leave it as 3/15. Let's do keep change flip to prove it. That's my original expression. I'm going to keep 3/5 as 3/5, but I'm going to change my division to multiplication. And once again, I'm going to take 3/1 and flip it upside down to 1/3. Numerator times numerator is 3. Denominator times denominator, 5 times 3 is 15. And it checks out. Okay, let's take a look at number 3. You have how many quarter hours are in 5 hours? I essentially have the same question, only just worded differently, where I'm trying to figure out how many half dollars there are in $5. Once again, it's a division. In this case, when you think about this, you have half dollars in $5. Is my answer going to be greater than 5 or less than 5? Well, let's see. We're going to take $5 and I'm going to make a tape diagram that's 5 pieces long. Each one is being divided up into halves. So watch here. Think of this as being $1 right here. This is $1. I have $1/2, $2/2. I'm going to do that here as well. There's 3 and $4/2. 5 and 6. 7 and 8. 9 and 10. There are 10 half dollars in 5 whole dollars. The way that question number 3 is different from 1 and 2 is that our answer, 10, is larger than what we started off with. What we're doing is really 5 divided by a half. And it will work if you do keep change flip. Here is keep change flip. Keep the first number, change division to multiplication, and flip the second fraction. 5 times 2 is 10. 1 times 1 is 1, and 10/1 as an improper fraction has to be changed back to a whole number, which indeed is 10. So let's just summarize. 1 and 2, you have a fraction divided by a whole number, whereas with number 3, you're doing a whole number divided by a fraction. And again, that will match up with the first 3 questions on your sheet. Just the names, I'm sorry, just the numbers and just the word problems themselves are different. Moving on to number 4. Number 4 is following the same plan and the same strategy as number 3. It's just now you have a word problem, but it's now still a whole number being divided by a fraction, much in the same way as number 3 was. And again, your question is different, but the concepts are going to be the same. Keywords: 4 pies divided into thirds. I'm going to make a tape diagram that is 4 segments long. I'm making it tall for a reason, because I've got to divide this up into thirds, and it just gives me a little bit more room. Each one is being divided into thirds. So we have a third here, second third, and 3 thirds per pie. Same thing here. And you can kind of see the pattern here. Once you realize the pattern, some kids like to just say, okay, I can count by 3s, 6, 9, and I can create 12 total slices if I do it this way. You can check it again with keep, change, flip. 4 is being divided by 1/3. We keep, we change, and we flip 1/3. That makes 12 over 1, which as a whole number is 12. Okay, that brings us to number 5. These could be tricky. That's why I suggest if we can use part to whole ratios, hopefully it'll work out for you. You have the Stacy question, I have the Kia question. It's essentially the same thing. We're going to create a template part to whole. We kind of did this when we did ratios, so it's somewhat of a refresher. I'm going to take the fraction that they give us, which is 6 over 9, and we're going to plug that into the template. 6 is the part for the entire ninths. You had 6 ninths, the 6 being the part, the 9 being the whole, whereas 9 ninths would be the whole thing. 6 out of 9, 6 becomes the part, 9 becomes the whole. And they tell us after 2 minutes, that 2 minutes is representing 6 ninths of how much is 6 ninths of the song that has been downloaded. So we have to kind of think to ourselves, well, 2 minutes is not the entire time, it's part of the time. So we're going to put the 2 on top. We're trying to figure out what the whole amount is. We actually need the whole amount first before we can determine how much longer it's going to take to download the remaining rest of the song. Once we have our 2 ratios, we need to take a look at the relationship with the 2 numbers that we have. 6 divided by 3 will give me 2. And then I'm going to do the same thing with my 9. 9 divided by 3 is 3. Now we have to be careful here. This is our part, this is our whole. It's telling me that it takes 3 entire minutes to download the whole song. So I'm not out of the woods yet. I need to figure out how much time is remaining. So I'm going to take the whole amount, which is 3. That's the entire time it takes. And I know that 2 minutes has already been downloaded. So I need to subtract that 2 minutes from my 3. And that tells me that there is 1 minute left on the download. Like I said, these are tricky questions, but always think part to whole ratio. When you have a fraction, you automatically have one entire ratio, and then you've got to determine where this piece goes. You have to determine whether that 2 minutes is representing a part or a whole. And then once you have both ratios set up, you're going to look at the relationship between each ratio and hopefully come up with an answer. Now, number 6 I'm not actually going to do, because really number 6 follows the same steps as number 5. You're going to do a part to whole ratio. You're going to substitute in your fraction. Figure out whether what they give you in the word problem is a part or a whole, and find your missing piece the same way. And we're going to move on to number 7. Our number 7s are going to differ slightly on yours. You're actually going to have to take that 1/8 that they give you, that 1/8 of a meter, and you're going to need to convert it into a common denominator of 16ths. So on yours, you got to make your 1/8 2/16 in order for this to make sense. On mine, I'm already in eighths, but I do have to make one change. I've got to change my mixed number into an improper fraction in order for this to work. So I'm going to do that now, and that becomes 14/8. Okay, my denominator tells me that I need to break up my number line into eighths. Starting with 0, this becomes 1/8, 2/8, and I need to get to 14/8, so I'm just going to keep going. Now, if you want, you could take a little bit of a shortcut. Since I know my denominator is in eighths, I'm just going to put my numerator. Until I get to the end, and I'll just kind of remind myself that's 14/8. I'm now going to take this fraction. This fraction tells me how to leap. I'm going to leap in leaps of 2/8. That's a leap of 2/8. That's another leap. And I'm going to keep going until I get to 14/8. Now all I need to do is count my leaps. And that is 7 leaps. And on my particular word problem, I'm cutting pieces of rope. So I want to say that 7 pieces of rope can be cut. Now, how does this relate to keep, change, flip? What this is 14/8, or 1 6/8 converted, being divided by 2/8. Watch how we can check this using keep, change, flip. Keep my 14/8 as is. Change division to multiplication. And flip 2/8 to 8/2. Now, if you remember, we can cross-reduce these 2/8. We learned this when we were doing multiplication and division of fractions. We can make these both 1. And I'm going to multiply 14 times 1, which is 14. And 1 times 2, which is 2. 14/2 is the same as the number 7. Now what I didn't do, which I'm seeing now, if you wanted to make it even easier, you could cross-reduce your 2 and your 14. They're both divisible by 2. The 2 goes into 2 once. It goes into 14 7 times. When you do this, you don't have to reduce it all. You got 7 times 1, which is 7. 1 times 1, which is 1. And 7/1 is the same as 7. When we get to number 8, we could go right to keep change flip. It's just a rehearsal and practice for what we've been doing to check our 1 through 7. I have 4 sevenths divided by 4 ninths. I know you have 3 sevenths and 3 fifths. Keep, change, and flip. And again, I want to show you, whenever you see an opportunity to cross-reduce cross products, you can do that. 4 goes into 4 once. And that's going to make 9 over 7, but we can't leave it like that. If you have a numerator that's bigger than a denominator, you got to change it back into a mixed number. 7 goes into 9 twice. Remember that our denominator always stays the same. And there are a remainder of 2. So that becomes our numerator. And so it's 2 and 2 sevenths. Moving on to number 9. We need to change this into an improper fraction first. So to do that again, it's 2 times 5 plus 1. Don't need this little 5 here. So 2 times 5 is 10, plus 1 is 11. Denominator stays the same. We're going to keep the division as division. I don't want to do keep, change, flip in the same step as changing to improper fractions. We'll do that in the next step. 1 times 7 is 7, plus 1 is 8. We have 8 sevenths. Okay, now we'll do keep, change, flip. Keep this as is. Change to multiplication. And flip to 7/8. Can we cross reduce? We cannot. So we've got to multiply through. 11 times 7 is 77. 5 times 8 is 40. Once again, we have a top-heavy fraction. We've got to change it back into a mixed number. 40 goes into 77 only once, with a remainder of 37. And our denominator stays the same. And then you always want to check 37/40. Is it in lowest terms? And it is in this case. So we're going to circle it. Now, if you look at number 10, 10's got an Easter egg next to it. I call these Easter eggs because this question appears exactly as it appears on your sheet. And if you've made it this far through the blog, you get a freebie on me. I'm actually going to do this for you. And as long as you copy it down step by step, you're automatically going to get the points for it. So here it is, your Easter egg. First one. There's going to be more. I'm going to change my whole number of 5 to 5 over 1. Again, don't attempt to do keep, change, flip and change improper fractions or mixed numbers into improper fractions in the same step. Do it step by step. 3 times 8 is 24. Plus 5 is 29. It's going to make 29 over 8. Now we'll do keep, change, flip. Keep this, change this, flip this. 8 times 5, 5 times 8 is 40. 1 times 29 is 29. Can we leave it like that? We can't. So we've got to change it into a mixed number. 29 goes into 40 once, with 11 left over, and you wind up getting 1 and 11/29. Going to skip number 11 and go to number 12, which is another Easter egg. 2 in a row. Don't get used to it though. 32 1/4 minus 10 1/2, exactly as it appears on your take-home sheet. And you're going to get a freebie. Once I do number 12, 11 and 13 on your sheet will follow pretty much the same pattern. The first thing we're going to do is change our fractions to decimals. 32 1/4. Well, 1/4 is in your fraction family. You should know that as 0.25. Minus 10 1/2, and also half is in your fraction family, and that is 0.5. We need to line up our decimals. Very, very important, in addition to subtraction of decimals, that the decimals line up, which I'm just going to show you there. We're subtracting. So 5 take away 0 is 5. Need to borrow a 2 here to make 12. 1 take away 0 is 1. 3 take away 1 is 2. And our final answer for you is 21.75. That's a freebie. One thing that I want to point out here, when creating your fractions, or I'm sorry, creating your decimals, and I'll give you a for instance. 6.9 minus, let's say, 3.84. When I set this up, I have to line up my decimals. Sometimes when you do this, you won't have a number here. And you need that, especially when you subtract. Anytime you do not see a number in that place, you want to fill it up with what's called an annex 0, so we can perform our subtraction or addition. More important when you do subtraction, to make sure that all of your place values are filled up with either the number that they give you, and if there is no number there, you want to fill up the empty nest with an egg. Okay, my number 14 matches up with your number 14, and again, I'm not actually going to do it, but it's going to follow the same procedure. You need to change your fractions into decimals. And in this case, I'm not going to tell you whether you should be adding or subtracting, but if you read the word problem, I think it'll make sense. So we're actually going to skip that one. You should be able to do that. And we'll now move on to number 15. All right, I found with number 15, these distributive property questions that appeared in module number 2. You did a pretty good job with this, so this is just going to be probably a quick refresher for you. The purpose of doing these particular problems in the Common Core is to try to see if you can break up numbers where you can multiply the numbers in your head. So given 200 times 10.8, the number that we're going to break apart is our 10.8. And here's how it's going to work. The 200 stays on the outside of the parentheses. And I believe on yours it's 300 times 20.7. This 10.8 gets broken up into 10 plus 0.8. The hope is to try to be able to multiply each of these numbers in your head, sort of, as we'll see. When you expand that now, that is really becoming 200 times 10 plus 200 times 0.8. Now the idea is to try to be able to do this in your head. Well, 200 times 10, you could use the 0 trick. That becomes 2,000. And you just have to be careful with 200 times 0.8, because 200 times 0.8 is going to produce a number that's less than 200, because 0.8 is less than 1. So as long as you could do 2 times 8 in your head, which is 16. And you know the number is slightly less than 200. We're hoping that you could see that that is 160. And if not, just do it off to the side, which I'll show to you again. You just have to remember you have to move your decimal in the product. Since we moved the decimal once here, we need to move it once here, and that's how I'm getting 160. And now I'm just going to add them together. My final answer is 2,160. Okay, moving on to multiplying decimals, where we're not going to line up decimals. We don't need to. Sometimes they'll line up by themselves naturally, but instead of lining them up, when we're done, we have to do something with the decimal in the product. So we'll do number 16, and you'll see with number 17, there's an Easter egg coming for you. When I set this up, it makes sense, like you've learned back in elementary school, that the number that has the most amount of digits should go on top, regardless of where the decimal is. So since there's 3 digits in 1.24 and only 2 digits in 3.9, put your 1.24 on the top. All right, so here we go. Just be sure to multiply carefully. Four times 9 is 36. We're going to carry the 3. 9 times 2 is 18, plus 3 is 21. Carry 2. 9 times 1 plus 2, 11. 3 times 4 is 12. 2, carry 1. 3 times 2 plus 1, 7. 3 times 1 is 3. And we're going to add them. Okay, we're almost done. To figure out where the decimal goes in the product, we need to take a look at the two original numbers we're multiplying. Since our decimal in 1.24 was moved twice to the left, I'm going to put a 2 here. And here, to go from the far right to where it is, was 1 move. That's a total of 3 moves. So, starting on the far right, I'm going to move my decimal 3 places. And that makes 4.836. And number 17 is an Easter egg for you. So you just need to follow exactly the way I do it here, because this is the same exact question as it is on yours. Once again, 3 digits compared to 2 digits. I'm going to put 12.1 on top, 0.8 at the bottom, but I'm actually going to drop the 0 because it's an insignificant figure. I don't need it. I'm just going to make it 0.8. And once again, the decimals don't have to line up, but sometimes they naturally do. That's okay. How many times have I moved the decimal here? Once. How many here? Once. That's a total of 2. 9.68 is your Easter egg for number 17. And I'm not going to do number 18 because I think you kind of get the idea of what to do. And you kind of get an Easter egg for 19. So let's do it. moving on to quotient, the first thing that you need to know is which is inside the house and which one's outside the house. And we should know that the second number is outside, and that's going to make 224.64 inside. I hope I have enough room here. It's going to be tight. All right. Next, we can't have a decimal outside the house. We've got to change this to a whole number. So to do that, we're moving the decimal once to the right. Whatever I do outside the house, I have to do inside the house. If I moved it once to the right, I got to do the same thing to my number inside. So my decimal goes between the 6 and the 4 and automatically raise it up in the roof and put it where it belongs. All right, now that everything is set up, I can't do 96 into 2 or 22, but it does go into 24, 224, 2 times. When I do 96 times 2 off to the side, I wind up getting 192. And I'm going to subtract, and that's going to leave a difference of 32. And I'm going to bring down my 6. 96 into 326 goes 3 times. And for me, that is going to make 288. Subtract my difference, I get 38. Bring down my 4. And 96 into 384 goes exactly 4 times. And when you have no remainder, it says it is considered to terminate. We have what's called a terminal number here. So my final answer is 23.4. Now your number 20 and my number 20 are the same. I'm not actually going to do it because the process is the same. I will give you a little hint and tell you that you're going to wind up with a repeating decimal for number 20. And if you need some help with that, I am available on Thursday morning and I'll help you with it. But that's, I'm not going to actually show you the repeating decimal and how that works. Hopefully you'll remember, but if not, certainly come on in. Okay, I'm going to show you how to do number 21. 21 is a unit rate question. With unit rate questions, I could do it with equivalent ratios if I wanted to. I could set this up as miles over hours and then plug in everything in. 398.25 takes 4.5 hours, and then you're trying to figure out what that would be for 1 hour, and you're trying to figure out how many miles it travels in that 1 hour. I think the easier way to do it, and a lot of kids will see it this way, is it's division. It's 4.5 into 398.25. And I just want to set that up for you because when you do it on yours is the plane traveling. The hours will go outside. The miles will go inside. Move your decimal over like I've shown you, and then just do it the same way as I've done it in the previous example. All right, so I just want to get you started with that, but I'm not actually going to go through the entire answer on my end here. So it's getting a little lengthy, the blog here. All right, we're almost done. We're home stretch. Let's do a GCF together. Then you've got an Easter egg, and then we'll do an LCM together, a couple LCMs, and we'll be good to go. All right, 22. Yours is the GCF of 18 and 90. Mine's 24 and 40 using prime factorization. When you see prime factorization, think factor trees. So I'm going to make a factor tree for 24. And I'm going to make a factor tree for 40. It doesn't matter what two numbers you start off with, you'll wind up with the same prime factors at the end. So I could go 12 and 2, I could go 8 and 3, and I can go 6 and 4. It doesn't matter. You'll still wind up with the same prime factors at the end. I'm going to go 6 and 4. Neither one of them are prime. 6 is a product of 3 and 2. Both of them are prime. We're going to circle them. Products of 4 are 2. Factors of 4 are 2 and 2. And those are my prime factors now for 24. Here comes 40. I'll start 8 and 5, 5 being prime. 8 breaks down to factors of 4 and 2. 2 is prime. And then 2 and 2 for 4. Now here's how it works. You're looking for prime factors, numbers that we've circled that are common in both trees. When you see it, cross them out in each tree, but only list it once. I see another 2 and another 2, but only list it once. Another 2 and another 2, list it once. I have nothing else that's common in the trees. So I've got 2 times 2 times 2, and if I multiply that, I get a GCF of 8. And that's how we do that. 23 is an Easter egg for you. So just follow what I do on your take home, and you'll automatically get credit. Two for 120. Doesn't matter how we start. I'm going to do 12 and 10. 12 breaks down. 6 and 2. 2 is prime. 6 is not. 3 and 2 make 6. 5 and 2 make 10. 120 is done. 144 happens to be 12 times 12. 12 breaks down to 4 and 3. Our 3s are prime, our 4s are not. All right, everything's broken down to prime factors. Look for common prime factors. I got a 3 and I got a 3. I'm going to list it once. I got a 2, got a 2. I'm going to list it once. Another 2. And another 2. I think that's it. That's it. All right, let's multiply. 3 times 2 is 6. 6 times 2 is 12. And 12 times 2 is 24. My GCF is 24. All right, let's do number 24. 24 is least common multiple. When I taught this to you, I told you if you have numbers that are like less than, let's say, 20, the easiest way to do 2 single-digit numbers is skip count. So here's my 6 and here's my 8. Remember that what LCM is you're finding a number that 6 and 8 can go into. Least common multiple has got to be the smallest number that 6 and 8 can go into. So we're going to count by 6s. I don't know how high I need to count, so I'm going to do a few. good enough for now. Let's do 8s. Now this you can do when you do it. If you want to look, as soon as we make a match, we don't need to go any further. And I make a match at 24. That's the lowest number that 6 and 8 can go into. So my LCM is 24. All right, now with number 25, I'm going to show you the second way to do this. Because we have numbers here now that are greater than 20. So counting by 14s and counting by 35s might, not only is it going to take longer, but there's more of a chance of you making a mistake. So I'm going to show you using prime factorization. Here's how that works. I'm going to make factor trees for 14 and 35. This breaks down to 7 and 2. Both are prime. 35 is 7 and 5. Both are prime. Here's where you got to be careful. First thing you're going to do is find a number that's common in both trees. And that's going to be our 7. I cross them both out. I list it once. This is my only common prime factor. But I'm not done. What LCM is, when you use prime factorization, it's the common factors listed once times the leftover prime factors. So we still have a 2 and we still have a 5. That's kind of like the junk, the leftovers, the waste, the extras, if you will, that we're going to tack on when we multiply all of our numbers together. So I'm going to take my 2, put it in, I'm going to take my 5 and put it in. This is now known as my leftovers. And now all I need to do is multiply 7 times 2 times 5, and that gets me my LCM, which is 70. Okay? Now once again, I can count by 14s. And I'll eventually get to 70. 35 will eventually get me to 70. The reason why I'm trying to show you this second way is if you make a mistake when you're counting by 14s, let's say you do 14, and then you do 28, and let's just say you do 44. Well, now you've counted incorrectly. So if you continue counting by 14s, you get 58, you get 72. Guess what? You never get to 70. You'll be counting forever. So whereas small numbers using this method, counting by small numbers will work, you have to be careful when the numbers start getting large, such as in this case, because if you count incorrectly, you're going to wind up not finding an LCM at all, or it might just take longer than it needs to. So that's why I suggest try prime factorization, common factors times leftovers. So that concludes Mod 2 review. And I will be available Thursday morning of this week. And then I have the due date for this being on Friday. So if you still need some help, I'm available Friday morning. Thursday morning at 7:15. And then, of course, the paper is due on Friday.